Hi everyone. So this week we're going to be covering a couple of topics from Chapter 5, namely Geometry and Trigonometry 2. And in this chapter we're going to be studying arc length and area of a sector. Now we're talking about circles. So in this example, what we have is a pizza, and they tell us that the pizza has a total area of 120 centimeters squared. The pizza is cut into 8 equal slices. This word is important, as shown in the diagram. A, what is the area of one slice? Okay, so this problem is pretty simple because if the whole pizza is 120 centimeters squared in area and it's cut into 8 equal slices, then each slice has to have an equal area. So that means that one slice has to be 120 divided by 8. And that equals 15. So 15, and don't forget the units, 15 we have to write centimeters squared. So that would be the answer for A. How about the total area for 3 slices? Well, if 15 is one slice, then certainly 3 times 15 would give us the total area of 3 slices. So this is equal to 45 centimeters squared. So in the next slide, what you're going to see is a circle and all the different elements of the circle that we have to be familiar with. So first of all, a circle has a center, and it has to be a center by definition, where you can draw any line from the center to the circle itself, and that line is going to equal a radius. So this line is a radius, just like this one is a radius as well. This green shaded region is what is known as a sector. So when we talk about sectors, we would be thinking of areas of, say, the slice of pizza. This here is known as the central angle. And it's always going to be a slice in terms of the whole circle, right? So this would be a piece of 360 degrees. Then, just as important is the definition of arc, because we're going to learn how to find arcs. And in this case, the arc that they are indicating starts here and ends here, right? So this section here, this part of the circumference, is an arc. Then sometimes you might have a line that does not go through the center. If there is a line, any line that goes through the center is known as a diameter. But if the line crosses the full circle and doesn't go through the center, then it's known as a chord. So this is a chord here. And this area that is cut out, so to speak, is known as a segment. So these are the parts of the circle that we need to be familiar with. Okay, so here we are on example 5.2. And it says, on golf courses, the grass is carefully watered to make sure that grass receives neither too much nor too little water. On a certain area of a golf course, a lawn sprinkler is set to spray an arc of 150 degrees with a spray distance of 3 meters. Calculate the area of grass that is watered by this sprinkler. Okay, so because we're talking about circles and areas, we have to remember the formula for the area of a circle. So that is that the area is equal to pi r squared. So this is what we would do to find the whole circle's area, right? But in this case, we only want a portion of it. So what portion do we want? Well, we want 150 out of 360. So this is a fraction of the circle that we need to find the area for. Therefore, we can find this particular sector's area by going 150 divided by 360 times pi r squared, in this case 3, so 3 squared. And then we plug that in the calculator, round it to 3 significant figures, and we're going to get 11.8 meters squared. Okay, everyone, so here we are now on example 5.3. And they're talking about some airplane routes that come very close to flying over the North Pole. The route from Dubai, United Arab Emirates, to Seattle, US of A, comes very close to the North Pole. In this case, the distance of the flight can be estimated by the arc length. Given that Dubai's airport is 25 degrees north and Seattle's airport is at 47.5 degrees north, as shown in the diagram, estimate the length of the flight between these two cities. The radius of the Earth is approximately 6,370 kilometers. Okay, part A, calculate the distance along the Earth's surface that the plane must travel. Now, remember that arc lengths are related to circumferences, because that's just a piece of the circumference. And let's recall that the circumference of a circle is given by 2 pi r as a formula. So really what they want us to find is a fraction of the total circumference. And that fraction is going to depend on the central angle. Now the central angle is not the 2 that they gave us, but rather this one here in between. And it's easy to find because we know that if this is the equator line, then it's splitting the Earth into 2 hemispheres. And that means that we're talking about 180 degrees, right, for the total hemisphere. Therefore, this has to be 180 minus 47.5 minus 25. And that would give us 107.5 degrees. So that means that we want to calculate 107.5 over 360 as a fraction of the total circumference. So this times 2 pi r, and r is going to be the radius of the Earth, which is approximately 6,370 kilometers. So let's plug this into the calculator, and we're going to see that it's going to give us approximately 11,952 kilometers. Okay, so that would be the answer to A, but how about the answer to B? Because in B, they changed the circumstances a little bit. Because they say that assuming the plane travels at a constant elevation of 10 kilometers above ground level, estimate the actual flight distance. So that means that we have to add another 10 kilometers here. And by doing that, what we really have to do is add 10 kilometers to the radius. So let's just substitute here in the formula, instead of a 7, or instead of 70, I'm going to write 80. So instead of 6370, let's use 6380 and calculate the result. So once we plug that in the calculator, we're going to get a number that is slightly higher, which is 11,970 kilometers. Okay, so in the next slide, you're going to find the beginning of exercise 5.1. So I'm going to ask you to please do these 7 exercises that all have the answers. And if you have any questions, I will be sending out a video on Wednesday explaining those questions. Okay, so here we are on topic 5.2, and it's the Voronoi diagrams. We did some exercise once with one of these. I don't know if you guys recall, with a whiteboard and stuff, but we're going to go a little bit into more detail of what these Voronoi diagrams are. And here we have an example of how they are used. So it says, emergency location services sometimes try to locate individuals based on their mobile phone signal. The first step in this process can be to locate the individual based on the nearest mobile phone antenna. A map to identify service regions for each mobile phone antenna would look like something on figure 5.3. So in this case, each red dot, that you can see here, is a mobile phone and tower. And the blue lines are the boundaries of each region served by that tower. So these are the boundaries, as we can see. So this is an example of what is called a Voronoi diagram. The polygons on the map, each of which shows the surface area for a particular mobile phone antenna, are called cells. So these are called cells. Now notice that it's a good name because they do follow a cellular pattern. They do look like a little bit like cells, where this would be the center of the cell, the nucleus of the cell, right? The dots represent mobile phone antennas and are called sites. So these are known as sites. The line segment boundaries between each region are called edges. And places where edges intersect are vertices. So this is an edge, and this is a vertice. An edge, vertice, edge, vertice. So here we have three edges on this vertice. Notice that some of the edges of cells around the outermost sites are actually rays and not line segments. So that means that here, this goes on. Okay, so this is a brief introduction to the Voronoi diagrams, and now we're going to actually solve some exercises with them. Okay, so here we are on example 5.4, and they say using the Voronoi diagram, A, identify the site closest to 30, 20. So we have to go to the grid here and look for 30, 20. So that's just the intersection point between these two lines, right? The one that starts here, 30 and 20, and we're going to see that that's going to land more or less here, right there. So this is within the cell that contains site A. So site A. Now the interesting thing about these Voronoi diagrams is that if you are within the cell, the closest site is going to be the site within the cell. And that's just because of how these things are built in principle. Basically, what I'm saying is that the way these are built is that you're going to have, for instance, this distance from A to this line at this point will equal the distance from D to that line as well, to that point on that line that separates the cells. Okay, and this line is called edge, remember. So this edge, if you draw a point on this edge, it's going to be equidistant from the point to A or the point to B, or the edge to A or the edge to B. We'll see why in a minute, okay? So it says here, give the coordinates of a vertex equidistant to 4 points. Now, precisely because all these points are equidistant, right? If I have a point on one of these edges, it's going to be equidistant to the sites within the bordering cells. But now all I have to do really is look for not an edge, but a vertex. And it has to be a vertex surrounded by 4 sites, or 4 dots. And we can see that that vertex is right here. It's this one. Because as you can see, that vertex is surrounded by sites M, F, G, C. And that vertex is at approximately 20, 5. So that would be the coordinates of that vertex. Part C says estimate the coordinates of a point equidistant to sites A, E, and K. So we need something that is close to E, A, and K. It has to be on all those 3 sites, cells, edges. Okay, what do I mean by that? So for example, here we have an edge that is shared by E and K, but not by A. But this vertex here is, right? That vertex is shared by E, A, and K, and therefore that point has to be equidistant to those 3 sites, A, E, and K. And let's estimate that coordinate. Now, please forgive me because I cannot see those lines too well, but it seems to be 19 here. And I'm going to guess about 26 and a half. So let's say 19, 26 and a half. Okay, part D, explain why the diagram cannot give us a point equidistant to sites C, F, I, and L. So let's look for C, F, I. Now I is far away. I and L. So that's the reason, right? It's out of range, so to speak. So I does not share any edges with the other cells. Letter E, point AA is equidistant to sites J and N. Find the value of A. So A has to be equidistant to J and N, and not only that, it has to be in the form A, comma A. Okay, so let's look for sites J and N, and we can see them up here. So this is J, and this is N. Now a point that is equidistant is somewhere here. But what we need it to have is coordinates that are the same. Notice that 40 is very close to that, right? 40. So here, if we take 40, we land on that edge, and let's see if that coincides with this other 40. Would it? Well, yeah, here's 40. And I think it would coincide. Yeah, definitely. So that means that A has to be 40 because that point there, this point here, is 40, comma 40. And because it's on the edge shared by J and N, it is definitely equidistant to both sites. And you can intuitively see it here on the graph. You can see that those distances are equal. Okay, for F, I'm going to use another slide because it's a totally different level of question. I mean, don't get me wrong, it's easy as well, but it requires a little more work. Okay, so here we are on another slide to solve part F of the question. So it says, find the equation of the edge between sites E and K in the form y equals mx plus c. So it's a linear equation. And we have to find sites E and K, which we can see that are here, right? E and K. So basically they want us to find the equation for this line, this edge. Now here's the interesting thing about these Voronoi diagrams, and it's that these edges dividing each one of these sites, no matter which edge you look at, it's going to be dividing the two sites that are perpendicular to that edge in an equidistance fashion. So what that means is really that this is just a perpendicular bisector of these 2 points, of points E and K, for example. That's the one we will have to find, right? So look, if I draw a line from E to K, I can see that it's perpendicular to their edge. And I want to find the equation of the edge. But I can use the slope of this line, the one that goes from E to K, to find the slope of the perpendicular. So let's do that. All right, so the slope from E to K would be 28 minus 18. Let's call this M1, slope 1. So 28 minus 18 over 8 minus 12, and this is going to equal 10 over negative 4, and this is simplified negative 5/2. Okay, so if this is the slope of the point between, or the line between points E and K, the perpendicular to this, which is M2, remember this property, if this is minus 5/2 and I multiply it by the slope of the perpendicular, it should equal negative 1. So if you solve for M2, you're going to see that it is the opposite reciprocal, or the reciprocal with the opposite sign, and that's positive 2 over 5. So that's the slope. So once we have the slope, all we need to do really is plug in a point on the line. But what point is on the line? They don't give us any points that are on the line. I'm talking about the perpendicular bisector. But we do know that this point here, the one that is on the intersection of the two lines, is the midpoint of E and K. So we can find that midpoint. And remember that midpoints are simply found by adding the coordinates and dividing them by 2. So the midpoint would be 8 plus 12 for x divided by 2. and the other one would be 28 plus 18 divided by 2. And therefore, the midpoint was going to be 20 divided by 2, 10, and 46 divided by 2, 23. So 10 comma 23 is the midpoint. And we can see that that's probably right, right? This is 10 here and 23 on the y-axis. So yes. So we have gathered enough information to finally write the equation, because the equation is in the form y equals mx plus c. We already have m. Y equals 2/5 x plus c, and all we need to do is find c, but we can use the point we just found to solve for c. Let's do that up here. So that would be 23 is equal to 2/5 x, 2/5 times x, sorry, that's times 10 plus c. We can solve this very quickly, and we can see that c is equal to 19. Okay, that means that we have the equation. I'm going to rewrite it somewhere here so it doesn't look so disorganized. So the answer would be y equals 2/5 x plus 19. So that would be the equation of the edges between those two sides, which is the perpendicular bisector. Okay, so the next slide goes into how to construct Voronoi diagrams. And they talk about a variety of algorithms or methods to construct them. And it talks about a method called the incremental insertion algorithm. Now that sounds awfully complicated, and they give you a series of steps and make it sound like it's very difficult. But basically what you do is that you choose a couple of sites, draw a perpendicular bisector between them, and then start building the new edges. And that's what we're going to see in the following example, which will explain this in a much easier fashion. Okay, so in example 5.5, they ask to show the process for adding the site shown in red to the Voronoi diagram. Okay, so basically we're going to see the process of building new walls or new edges for this site. So notice here that we have the first step, which is simply to identify the nearest site. So in this case, we identify this one. And step 2, add a perpendicular bisector, which you do as a dotted line. And then the third step is that you use that perpendicular bisector to create a line segment, but the endpoints are going to be on existing cell boundaries. So you go from this cell boundary down to this one, and you simply build that edge. So the reason this is called an algorithm is because you repeat the same process over and over. So what we have to do is choose another site and draw a perpendicular bisector. So in this case, notice that this is the other site chosen, and the dotted line is a perpendicular bisector. Following that, we draw the segment, but from one edge to the other. So that's why you start here at this edge and then continue down to this other edge and stop there. This was the one that we drew previously. Okay, and as an algorithm, it repeats itself. And we do the same process again, but we choose this other site, and notice that the dotted line is the perpendicular bisector. Then we continue with the same process by drawing the line segment from edge to edge, from here to there. Notice that we had these two before. And then finally, the last site that we have to draw a perpendicular bisector with is this one. Draw another line segment from edge to edge, and we end up with the figure. Now the last step would be to get rid of the edges that are inside, and that's what we're going to see on the next slide. And there you go, you can see the new cell that fits perfectly into the figure, and after we have removed all the edges that were inside. Okay, so here we are in example 5.7, where they ask us to create a Voronoi diagram for the points A, B, C, and D. So in this one, basically they're asking us to create the diagram from scratch. So the first step is choosing 2 points. So we're going to choose A and B. And then the next step would be to build the perpendicular bisector between A and B. And we're not going to even use any algebraic equations or anything. It's just going to be a drawing where you have a line that you know is a perpendicular bisector between A and B, and you should get something like that. And then this line is made continuous because this is going to be the first edge. Okay, next, another perpendicular bisector between points A and C. So between points A and C, you get that perpendicular bisector. And then you're going to draw a line segment that starts on the x-axis and ends on the already existing edge, and you get this. Now, we should build another perpendicular bisector between C and B, and this is what you get. So that's a perpendicular bisector between C and B. It happens to go through point D, but that's just a coincidence. As we do this, we have to get rid of any part of the perpendicular bisector that is not necessary, right? That is not necessary. And also we have to draw the red line, and this is what we get. Okay, so we have to get rid of sections of these lines that have no function, like that extra segment which is within the cell for site C. So we should get something like that. So now we have the actual cell walls, but we're still missing something to separate sites B and D. And there we go. Also, we built another perpendicular bisector between sites C and D. Very well. So on the next slide, we're going to see a reference to something called nearest neighbor interpolation. And that is simply a common use of the diagrams, of the Voronoi diagrams, which is to assign values to points based on the nearest site. So this is called the nearest neighbor interpolation. And that's what we're going to go over next. It sounds much more complicated than what it actually is. As we're going to see in the next slide, it's actually fairly simple. So, for example, consider the map in figure 5.5. In the map, we can see measurements from rain collection gauges on 27 July 2017 in Pueblo, Colorado, USA. The measurements are given in inches. If we want to estimate the rainfall at a location near one of the rainfall gauges, we can simply use the nearest gauge. Okay, so if you look at the map, the lines are not edges of cells. These are actually road maps. So that means that if we had to answer something like this, we would have to build the Voronoi diagram. And that is precisely what they ask us to do in example 5.8, where they say use the map of rainfall measurements in figure 5.5 to estimate the rainfall at the coordinates P 6,4. So let's suppose we did it all. Let's just go to the solution. And you can see that here they have the actual cells and edges around the sites of the Voronoi diagram. And point P is right here, which is in the cell that contains this guy here. And that site is 0.63. So that would mean that we could estimate that for site P, the rainfall would be 0.63 inches. So that would be all for this week. I hope you also remember to do exercise 5.2. We have a series of other questions that you need to solve. All the solutions are here in the document. So you really don't even have to go and look for them. You can just work with this document that I'm sending you. If you have any questions resulting from your practice, then send them to me and I will be making a video that I'll post next Wednesday. So good luck to everybody. Wish you the best. Bye-bye.